the relatively static membrane potential of quiescent cells is called the resting membrane potential, as opposed to the specific dynamic electrochemical phenomena called action potential and graded membrane potential. Apart from the latter two, which occur in excitable cells, membrane voltage in the majority of non-excitable cells can also undergo changes in response to environmental or intracellular stimuli. In principle, there is no difference between resting membrane potential and dynamic voltage changes like action potential from a biophysical point of view. All these phenomena are caused by specific changes in membrane permeabilities for potassium, sodium, calcium, and chloride ions, which in turn result from concerted changes in functional activity of various ion channels, ion transporters, and exchangers. Conventionally, resting membrane potential can be defined as a relatively stable, ground value of transmembrane voltage in animal and plant cells. Any voltage is a difference in electric potential between 2 points. For example, the separation of positive and negative electric charges on opposite sides of a resistive barrier. The typical resting membrane potential of a cell arises from the separation of potassium ions from intracellular, relatively immobile anions across the membrane of the cell. Because the membrane permeability for potassium is much higher than that for other ions, and because of the strong chemical gradient for potassium ions flow from the cytosol into the extracellular space carrying out positive charge, until their movement is balanced by buildup of negative charge on the inner surface of the membrane. Again, because of the high relative permeability for potassium, the resulting membrane potential is almost always close to the potassium reversal potential. But in order for this process to occur, a concentration gradient of potassium ions must first be set up. This work is done by the ion pumps, transporters and/or exchangers and generally is powered by ATP. In the case of the resting membrane potential across an animal cell's plasma membrane, potassium gradients are established by the Na+/K+- H base, which transports 2 potassium ions inside and 3 sodium ions outside at the cost of 1 ATP molecule. In other cases, for example, a membrane potential may be established by acidification of the inside of a membranous compartment. Electro neutrality, in most quantitative treatments of membrane potential, such as the derivation of Milman Equation, electro neutrality is assumed. That is, that there is no measurable charge excess in any side of the membrane. So, although there is an electric potential across the membrane due to charge separation, there is no actual measurable difference in the global concentration of positive and negative ions across the membrane, that is, there is no actual measurable charge excess in either side. That occurs because the effect of charge on electrochemical potential is hugely greater than the effect of concentration, so an undetectable change in concentration creates a great change on electric potential. Generation of the resting potential, cell membranes are typically permeable to only a subset of ions. These usually include potassium ions, chloride ions, bicarbonate ions, and others. To simplify the description of the ionic basis of the resting membrane potential, it is most useful to consider only one ionic species at first, and consider the others later. Since transplasma membrane potentials are almost always determined primarily by potassium permeability, that is where to start. Panel 1 of the diagram shows a diagrammatic representation of a simple cell where a concentration gradient has already been established. This panel is drawn as if the membrane has no permeability to any ion. There is no membrane potential, because despite there being a concentration gradient for potassium, there is no net charge imbalance across the membrane. If the membrane were to become permeable to a type of ion that is more concentrated on one side of the membrane, then that ion would contribute to membrane voltage because the permeant ions would move across the membrane with net movement of that ion type down the concentration gradient. There would be net movement from the side of the membrane with a higher concentration of the ion to the side with lower concentration. Such a movement of one ion across the membrane would result in a net imbalance of charge across the membrane and a membrane potential. This is a common mechanism by which many cells establish a membrane potential. In panel 2 of the diagram, the cell membrane has been made permeable to potassium ions, but not the anions inside the cell. These anions are mostly contributed by protein. There is energy stored in the potassium ion concentration gradient that can be converted into an electrical gradient when potassium ions move out of the cell. Note that potassium ions can move across the membrane in both directions, but by the purely statistical process that arises from the higher concentration of potassium ions inside the cell, there will be more potassium ions moving out of the cell. Because there is a higher concentration of potassium ions inside the cells, their random molecular motion is more likely to encounter the permeability pore than is the case for the potassium ions that are outside and at a lower concentration. An internal K+ is simply more likely to leave the cell than an extracellular K+ is to enter it. It is a matter of simple diffusion doing work by dissipating the concentration gradient. As potassium leaves the cell, it is leaving behind the anions. Therefore a charge separation is developing as K+ leaves the cell. This charge separation creates a transmembrane voltage. This transmembrane voltage is the membrane potential. As potassium continues to leave the cell, separating more charges, the membrane potential will continue to grow. The length of the arrows represents the magnitude of potassium ion movement due to each form of energy. The direction of the arrow indicates the direction in which that particular force is applied. Thus, the building membrane voltage is an increasing force that acts counter to the tendency for net movement of potassium ions down the potassium concentration gradient. In panel 3, the membrane voltage has grown to the extent that its strength now matches the concentration gradients. Since these forces are now the same strength and oriented in opposite directions, the system is now in equilibrium. Put another way, the tendency of potassium to leave the cell by running down its concentration gradient is now matched by the tendency of the membrane voltage to pull potassium ions back into the cell. K+ continues to move across the membrane, but the rate at which it enters and leaves the cell are the same, thus, there is no net potassium current. Because the K+ is at equilibrium, membrane potential is stable, or resting. The resting voltage is the result of several ion translocating enzymes in the plasma membrane, steadily operating in parallel, whereby each ion translocator has its characteristic electromotive force, depending on the particular substrate concentrations inside and outside. H+ exporting at base render the membrane voltage in plants and fungi much more negative than in the more extensively investigated animal cells, where the resting voltage is mainly determined by selective ion channels. In most neurons the resting potential has a value of approximately 70 MV. The resting potential is mostly determined by the concentrations of the ions in the fluids on both sides of the cell membrane and the ion transport proteins that are in the cell membrane. How the concentrations of ions and the membrane transport proteins influence the value of the resting potential is outlined below. The resting potential of a cell can be most thoroughly understood by thinking of it in terms of equilibrium potentials. In the example diagram here, the model cell was given only one permeant ion. In this case, the resting potential of this cell would be the same as the equilibrium potential for potassium. However, a real cell is more complicated, having permeabilities to many ions, each of which contributes to the resting potential. To understand better, consider a cell with only two permeant ions, potassium and sodium. Consider a case where these two ions have equal concentration gradients directed in opposite directions, and that the membrane permeabilities to both ions are equal. K+ leaving the cell will tend to drag the membrane potential toward Ek. Now plus entering the cell will tend to drag the membrane potential toward the reversal potential for sodium Na. Since the permeabilities to both ions were set to be equal, the membrane potential will, at the end of the Na+/K+ tug of war, end up halfway between Na and Ek. As Na and Ek were equal but of opposite signs, halfway in between is 0, meaning that the membrane will rest at 0 MV. Note that even though the membrane potential at 0 MV is stable, it is not an equilibrium condition because neither of the contributing ions are in equilibrium. Ions diffuse down their electrochemical gradients through ion channels, but the membrane potential is upheld by continual K+ influx and Na+ efflux via ion transporters. Such situation with similar permeabilities for counteracting ions, like potassium and sodium in animal cells, can be extremely costly for the cell if these permeabilities are relatively large, as it takes a lot of ATP energy to pump the ions back. Because no real cell can afford such equal and large ionic permeabilities at rest, resting potential of animal cells is determined by predominant high permeability to potassium and adjusted to the required value by modulating sodium and chloride permeabilities and gradients. In a healthy animal cell, Na plus permeability is about 5% of the K plus permeability or even less, whereas the respective reversal potentials are plus 60 MV for sodium under 80 MV for potassium. Thus the membrane potential will not be right at EK, but rather depolarized from EK by an amount of approximately 5% of the 140 MV difference between EK and ENA. Thus, the cell's resting potential will be about a 73 MV. In a more formal notation, the membrane potential is the weighted average of each contributing ion's equilibrium potential. The size of each weight is the relative conductance of each ion. In the normal case, where 3 ions contribute to the membrane potential, where M is the membrane potential, measured in volts, X is the equilibrium potential for ion X, also in volts, Gx is the relative conductance of ion X in arbitrary units, Gtot is the total conductance of all permeant ions, in this case Gk++ Gna++ Gcla. Membrane transport proteins. For determination of membrane potentials, the two most important types of membrane ion transport proteins are ion channels and ion transporters. Ion channel proteins create paths across cell membranes through which ions can passively diffuse without direct expenditure of metabolic energy. They have selectivity for certain ions, thus, there are potassium, chloride, and sodium selective ion channels. Different cells and even different parts of one cell will have different amounts of various ion transport proteins. Typically, the amount of certain potassium channels is most important for control of the resting potential. Some ion pumps such as the Na+/K+- H base are electrogenic, that is, they produce charge imbalance across the cell membrane and can also contribute directly to the membrane potential. Most pumps use metabolic energy to function. Equilibrium potentials. For most animal cells, potassium ions are the most important for the resting potential. Due to the active transport of potassium ions, the concentration of potassium is higher inside cells than outside. Most cells have potassium-selective ion channel proteins that remain open all the time. There will be net movement of positively charged potassium ions through these potassium channels with the resulting accumulation of excess negative charge inside the cell. The outward movement of positively charged potassium ions is due to random molecular motion and continues until enough excess negative charge accumulates inside the cell to form a membrane potential which can balance the difference in concentration of potassium between inside and outside the cell. Balance means that the electrical force that results from the buildup of ionic charge, and which impedes outward diffusion, increases until it is equal in magnitude but opposite in direction to the tendency for outward diffusive movement of potassium. This balance point is an equilibrium potential as the net transmembrane flux of K+ is zero. A good approximation for the equilibrium potential of a given ion only needs the concentrations on either side of the membrane and the temperature. It can be calculated using the Nernst equation, where eq. K+ is the equilibrium potential for potassium, measured in volts, R is the universal gas constant, equal to 8.314 joules per K1 a mole 1, T is the absolute temperature, measured in kelvins, Z is the number of elementary charges of the ion in question involved in the reaction, F is the Faraday constant, equal to 96,485 coulombs a mole 1 or Java 1 a mole 1. K plus O is the extracellular concentration of potassium, measured in molar Ma 3 or molar 1, K plus. I is likewise the intracellular concentration of potassium. Potassium equilibrium potentials of around 80 mV are common. Differences are observed in different species, different tissues within the same animal, and the same tissues under different environmental conditions. Applying the Nernst equation above, one may account for these differences by changes in relative K+ concentration or differences in temperature. For common usage, the Nernst equation is often given in a simplified form by assuming typical human body temperature, Reducing the constants and switching to log base 10 for potassium at normal body temperature, one may calculate the equilibrium potential in millivolts as. Likewise, the equilibrium potential for sodium at normal human body temperature is calculated using the same simplified constant. You can calculate E assuming an outside concentration, K plus O, of 10 mm and an inside concentration, K plus I, of 100 mm. For chloride ions, the sign of the constant must be reversed. If calculating the equilibrium potential for calcium, the 2 plus charge halves the simplified constant to 30.77 MV. If working at room temperature, about 21 degrees Celsius, the calculated constants are approximately 58 MV for K plus and Na plus, 58 MV for Cl and 29 MV for Ca2 plus. At physiological temperature, about 29.5 degrees Celsius, and physiological concentrations, the calculated potentials are approximately 67 MV for Na plus, and 90 MV for K plus, and 86 MV for Cl and 123 MV for Ca2 plus. Resting potentials. The resting membrane potential is not an equilibrium potential as it relies on the constant expenditure of energy for its maintenance. It is a dynamic diffusion potential that takes this mechanism into account, wholly unlike the equilibrium potential, which is true no matter the nature of the system under consideration. The resting membrane potential is dominated by the ionic species in the system that has the greatest conductance across the membrane. For most cells this is potassium. As potassium is also the ion with the most negative equilibrium potential, usually the resting potential can be no more negative than the potassium equilibrium potential. The resting potential can be calculated with the Goldman-Hodgkin-Katz voltage equation using the concentrations of ions as for the equilibrium potential while also including the relative permeabilities of each ionic species. Under normal conditions, it is safe to assume that only potassium, sodium and chloride ions play large roles for the resting potential. This equation resembles the Nernst equation, but has a term for each permeant ion. Also, Z has been inserted into the equation, causing the intracellular and extracellular concentrations of Cl to be reversed relative to K plus and Na plus, as chloride's negative charge is handled by inverting the fraction inside the logarithmic term. M is the membrane potential, measured in volts R, T, and Fr as above. Ps is the relative permeability of ion S, Y is the concentration of ion S in compartment Y as above. Another way to view the membrane potential, considering instead the conductance of the ion channels rather than the permeability of the membrane, is using the Milman equation. Or reformulated, where GTOT is the combined conductance of all ionic species, again in arbitrary units. The latter equation portrays the resting membrane potential as a weighted average of the reversal potentials of the system, where the weights are the relative conductances of each ion species. During the action potential, these weights change. If the conductances of Na plus and Cl are zero, the membrane potential reduces to the Nernst potential for K plus. Normally, under resting conditions G-Na plus and G-Cla are not zero, but they are much smaller than Gk plus, which renders M close to weak, K plus. Medical conditions such as hyperkalemia in which blood serum potassium is changed are very dangerous since they offset EK, K plus, thus affecting M. This may cause arrhythmias and cardiac arrest. The use of a bolus injection of potassium chloride in executions by lethal injection stops the heart by shifting the resting potential to a more positive value, which depolarizes and contracts the cardiac cells permanently, not allowing the heart to repolarize and thus enter diastole to be refilled with blood. It should be noted that while the GHK voltage equation and Milman's equation are related, they are not equivalent. The critical difference is that Milman's equation assumes the current voltage relationship to be ohmic, whereas the GHK voltage equation takes into consideration the small, instantaneous rectifications predicted by the GHK flux equation caused by the concentration gradient of ions. Thus, a more accurate estimate of membrane potential can be calculated using the GHK equation than with Milman's equation. Measuring resting potentials. In some cells, the membrane potential is always changing. For such cells there is never any rest, and the resting potential is a theoretical concept. Other cells with little in the way of membrane transport functions that change with time have a resting membrane potential that can be measured by inserting an electrode into the cell. Transmembrane potentials can also be measured optically with dyes that change their optical properties according to the membrane potential. Summary of resting potential values in different types of cells. See also, action potential, depolarization, hyperpolarization, membrane potential. References. External links, Neuroscience, online textbook by Purvis, et al. Basic Neurochemistry Molecular, Cellular, and Medical Aspects by Siegel, et al. Bertil Hill Ion Channels of Excitable Membranes, 3rd ed., Scheinauer Associates, Sunderland, M.A. ISBN 0-87893-321-2, Generation of Resting Membrane Potential Wright, S.H., Advances in Physiology Education, 28, 1 139 142, 2004, Resting Membrane Potential, online lecture notes on the resting membrane potential, the origin of the resting membrane potential, online interactive tutorial.